Alright, let's go. Number 11, the turbulence puzzle. You see it almost every single day of your life. When you pour cream into your coffee and watch it bloom into chaotic spirals, when a plane jolts unexpectedly at 30,000 feet, when smoke curls upward and dissolves into the night air. It feels random, but controlled. Here is the quiet, embarrassing secret. We do not have a mathematical proof that we truly understand it. The Navier-Stokes equations, written nearly 2 centuries ago, are supposed to describe how fluids move. Engineers rely on them to design jet engines and predict blood flow, yet no one can prove these equations always produce smooth, stable solutions. Under certain conditions, the math might break and explode into infinities. Think about that. We can detect black hole collisions across the universe, but we cannot guarantee what water will do inside a simple pipe. The chaos in your coffee may be deeper than we admit. Number 10. The hierarchy problem. Grab a cheap refrigerator magnet and hold it just above a heavy iron nail resting on a table. The nail leaps upward and clicks into place. It feels trivial, but in that instant, you witness something that should not make sense. Every atom of the Earth, nearly 6 septillion kilograms of mass, was pulling that nail downward with gravity, and your tiny magnet still won. Gravity is weaker than electromagnetism by a factor of 10 to the 36th power, a 1 followed by 36 zeros. The strong force, the weak force, and electromagnetism fit together with an elegant mathematical symmetry. Gravity is the emaciated outlier. If it were slightly stronger, stars would burn out in years. Slightly weaker, galaxies would never form. Some theorists suggest gravity is leaking into hidden extra dimensions, leaving us with only a diluted shadow. What we call weight may be a faint residue of something far greater. Number 9. The impossible marriage. Modern physics stands on 2 absolute pillars. On one side is Einstein's general relativity, the theory of the unimaginably massive. It explains how stars move, how galaxies rotate, how gravity bends the very fabric of space and time. It is elegant, predictable, precise. On the other side is quantum mechanics, the theory of the unimaginably small, where particles exist as probabilities and certainty dissolves into statistics. Both have been proven correct by countless experiments. They are the greatest intellectual achievements in human history, and they absolutely hate each other. The moment you try to combine their mathematics, the equations self-destruct. They produce infinities, they output nonsense. Inside black holes and at the first instant of the Big Bang, reality demands one unified rulebook. We do not have it. Deep down, nature knows a single truth that binds the giant and the microscopic, and it remains locked behind a wall of contradiction. Number 8. The strong CP problem. To understand this nightmare, you have to shrink down into the nucleus of an atom, where the strong nuclear force binds protons and neutrons together. In particle physics, there is a principle called CP symmetry. Swap a particle with its antimatter twin, mirror its spatial coordinates, and the laws of physics should remain the same. The weak nuclear force violates this symmetry regularly. It shows preference, but the strong force obeys CP symmetry with a terrifying, flawless precision. The mathematics of quantum chromodynamics allows a large violation. It predicts the neutron should carry a tiny electric dipole moment, an internal imbalance, yet decades of exquisitely sensitive experiments have found nothing. The neutron is balanced to 1 part in 10 billion trillion. A parameter called theta could range from 0 to 360 degrees. Somehow, the universe has tuned it exactly to 0. Physicists proposed a new particle, the axion, to sweep this imbalance away. After decades of searching, it has never appeared. Number 7. The magnetic ghost. Take a simple bar magnet, it has a north pole and a south pole. Cut it perfectly in half, and you do not get a lone north and a lone south. You get 2 smaller magnets, each with their own pair of poles. Cut them again and again, all the way down to the atomic level, and the rule never changes. Magnetic poles always come in pairs, but grand unified theories predict something very different. In the blistering heat of the early Big Bang, the universe should have forged magnetic monopoles, isolated north or south poles wandering alone through space. The mathematics demands their existence. Paul Dirac proved that even one monopole would explain why electric charge is quantized. The logic is beautiful. Yet after decades of searching the cosmos, lunar rocks, and particle collisions, none have been found. Inflation may have diluted them beyond detection, but that feels like a mathematical bandage. The equations insist they exist, reality remains silent. Number 6. The lightweight mystery. Right now, as you listen to this, trillions of invisible particles are passing through your body. They stream from the core of the sun, cross the vacuum of space, slip through your walls, your skin, your brain, and continue into the earth without touching a single atom. They are called neutrinos. For decades, the Standard Model declared they had exactly 0 mass, moving forever at the speed of light. Then in 1998, massive underground detectors in Japan observed something impossible. Neutrinos change flavor as they travel. Electron, muon, tau, they oscillate. For a particle to change state, time must pass, and if time passes, it cannot travel at light speed. It must have mass. The discovery won the Nobel Prize and shattered the model. The Higgs field explains mass for other particles, but not for neutrinos. their tiny weight points to a hidden layer of physics beneath reality. Number 5. The lithium problem. Let's rewind 13.8 billion years to the first 3 minutes after the Big Bang. The universe was a superheated furnace where protons and neutrons fused in a process called Big Bang nucleosynthesis, using well-tested nuclear physics. Scientists can calculate exactly how much hydrogen, helium, and lithium should have formed in that primordial blaze. When we examine the oldest stars in the galaxy, hydrogen matches perfectly, helium matches beautifully, but lithium-7 does not, according to the equations. A precise amount should exist. Instead, we find only about 1/3, 2/3 of the universe's primordial lithium is missing. It is a cosmic accounting error. Did we misunderstand the nuclear physics of the early universe? Did dark matter interact and quietly destroy the lithium? Or do ancient stars slowly consume it over billions of years? Either way, a crack runs through our origin story, and it has not been sealed. Number 4. The proton's immortality. Everything fades, mountains erode into dust, stars exhaust their fuel and collapse, even black holes will eventually evaporate over unimaginable stretches of time. But what about the proton? Protons anchor the nuclei of atoms, they make up your screen, your air, your body. According to the Standard Model, they are perfectly stable, they last forever. Yet most grand unified theories predict that, given enough time, a proton must decay into lighter particles. If that is true, matter itself has an expiration date. Trillions upon trillions of years from now, the universe would dissolve into a thin mist of radiation. To test this, scientists built Super Kamiokande in Japan, a cavern holding 50,000 tons of ultra-pure water, watching for a single flash of decay. They have seen nothing. The proton's half-life is at least 10 to the 34th power years, a number dwarfing cosmic history. Is it truly immortal, or are we simply too early? Number 3. The measurement curse. This is where physics crosses into something deeply unsettling. In the quantum world, particles like electrons do not exist in a single location, they exist as a wave function, a haze of probabilities, mathematically everywhere and nowhere at once. The double-slit experiment proves it. Fire electrons through 2 slits and they behave like waves, passing through both simultaneously and forming an interference pattern, but place a detector at the slits, try to see which path the electron takes, and the wave function collapses. The interference vanishes, the electron behaves like a solid particle choosing one route. How does a mindless particle know it is being watched? Schrödinger mocked this with his cat, alive and dead until observed. The joke became reality. We have no equation explaining collapse. It suggests objective reality may not exist until perceived, that the universe is a soup of probabilities solidifying only because we are here to witness it. Number 2. The unreasonable perfection. This is the grand finale. When you peel back reality, you find a control panel of fundamental constants: the mass of the electron, the strength of gravity, the speed of light, the density of dark energy. These numbers have no deeper explanation. They are simply brute facts, yet if you adjust any one of them by even a fraction, the universe collapses. If the strong force were 2% stronger, atoms could not form. If gravity were slightly weaker, stars and galaxies would never gather. If the cosmological constant were larger by 1 part in 10 to the 120th power, expansion would outrun structure entirely. The precision required is like throwing a dart from Earth and hitting a bullseye at the edge of the observable universe. Is it coincidence, a multiverse selection effect, or evidence of a design simulation? We do not know. We only know the dials are set with terrifying perfection, and we are living inside it. Number 1. The silence between the equations. After everything we've just walked through, there is one more problem hiding in plain sight. Not a missing particle, not a broken symmetry, not a cracked equation, but the silence between them. Physics gives us models that work with astonishing precision. They predict eclipses, particle collisions, gravitational waves. Yet again and again, we find limits. Turbulence resists proof. Gravity feels unnaturally weak. Quantum mechanics refuses to merge with relativity. Constants sit perfectly tuned without explanation. It is as if reality allows us to see the surface, but never the foundation. The deeper we look, the more the answers become placeholders for a deeper question. Why do these equations exist at all? Why is there something rather than nothing? We have no framework for that, just a widening boundary where mathematics stops and mystery begins. If this kind of quiet uncertainty fascinates you, consider subscribing and staying with us as we keep exploring the cracks in reality together.